My name is János Csirik, and I am an emeritus professor of University Szeged in Hungary. It is a great pleasure to welcome you at this beanpacking seminar. COVID-19 has changed our life in many ways. We have less opportunities to meet friends, colleagues, less opportunities to travel. Online conferences offer different possibilities as usual offline conferences. Probably the time spent for teaching is increasing for everybody. We are sitting more at our computers. These changes are not so good, but perhaps we may have new possibilities too. This seminar is an attempt to use the new circumstances in a good direction. To let the researchers who are working on closely related fields meet regularly for a time period and to give an overview about their research, so inspiring further joint work. I hope this will be successful. I would like to thank Asaf Levin for setting up the Zoom for the seminar, Arindam Khan for managing the website, and Lea Epstein, Asaf Levin, and Silvano Martello for preparatory conversations on and their ideas. And now I give the Zoom for Asaf Levin to give the first talk. Asaf is working at Technion. Asaf.
Yes. So now we are more practiced in this Zoom stuff. We are more ready to give talks using the Zoom. So I will talk about approximation schemes for the extension or generalization of the extensible beanpacking problem. I will consider both a scheduling variant and a beanpacking variant. Okay, so you could imagine why I need a beanpacking variant, mainly because we are in the beanpacking seminar. The scheduling variant is the one which was studied before. Is defined as follows. We have jobs, and we need to schedule the jobs on machines. So the jobs are indexed 1 to up to n, and a job has a size, pj. And we have n machines. But this time, these are not really identical machines because each machine has a different cost function. So, and the cost function of a given machine is specified by 3 constants: the fixed cost, Fi, the capacity or standard capacity, Ti, and cost for overtime, sigma I. So in this figure, you could see the cost function. This is this line. Right? And the fixed cost is the cost of a machine if the total size of jobs assigned to that machine is smaller than the capacity Ci. And then the cost of the machine grows linearly with the slope of sigma. So this is this strange formula here. If the cost of a machine is the fixed cost, if the load assigned to that machine is smaller than the capacity, and afterwards it grows linearly with the slope of or rate of sigma. And these 3 constants are per machine. And the goal is to find the partition of the jobs to the n machines. So we would like to consider non-preemptive schedules. That is a partition of the jobs. And after we define the partition, we compute the load of each machine, and we would like to minimize the total cost of all machines. The assumptions that we need to make in order to present some bounded approximation algorithm is that we have some ratio between the fixed cost and the product of the sigma I and Ci. Otherwise, we will allow functions that grows here very fast, and then an optimal solution pays only the fixed cost, the total fixed cost, if and only if a tripartition instance is feasible. And otherwise, the cost will be enormous. So in order to get a bounded approximation algorithm, we need a way to bound the slope of this line in terms of this line. It has to be by at most a constant factor, and it doesn't really change the problem if the scheme that you get if you assume that this is the product, the fixed cost is the product of sigma I and Ci. So far is the scheduling part. The bin packing variant is defined very similarly, except the fact that they tried to replace job by items. And instead of machines, we have bin types. And the idea is that in this bin packing variant, the algorithm can decide to buy the machines. And to buy a machine means to specify what is the fixed cost and what is the capacity and overtime. It has to be a triple of one of the bin types of the input. And we pay for the machines that we decide to buy. For the bin packing variant, we don't need the assumption that the fixed cost is the product of sigma I and Ci. And I will show you how to deal without this assumption. Okay, before we continue, let me tell you something. I'm an Israeli and I teach in Israel, which means that I will not be offended by any interruption by the audience, because trust me, you are not able to do anything that will surprise me. So please, if you have questions, do not wait until the end. Simply unmute yourself and ask. So if there are any questions about problem definition, I would be happy to answer. Otherwise, I will continue on.
Can you clarify again the cost function? You mentioned cost minus IL to be the cost, or the cost is equal to cost? So there is two terms, cost minus IL.
Okay, so the cost I of a bin of type I, if I decide to assign total size of L to this bin, is the
It's
fixed.
not subtraction sign. I was confusing with this cost. It's hyphen, not subtraction sign. Or
not subtraction, you know. No, both for the scheduling and for the bin packing variant. Okay, so the cost for one specific bin is defined in terms of the total size of items I assign to this bin. It needs to be at most the total size of all the items. So I don't require bins to be total size at most one or something like that. And we have a cost for each way to get a subset of the items into one bin of this type. And it looks like and here, this line need not be the continuation of the blue line here. So this need not be the continuation of it. So you can go very fast, very small, very steep, or very non-stick, I don't know. And different types could lead to very different slopes. So, for example, it could have the same fixed cost but different slopes. This is for the beam packing type. Okay.
Sorry, I have a question. So in the beam packing problem, that means each tab has infinite number of beams, is it?
Yes, you could assume at most n copies that you could use if you want.
Okay, thank you.
Okay, there's no point in having an empty beam. Okay, so what are approximation schemes? And I hope that you will be able to follow. A polynomial time algorithm that always returns a feasible solution, of course, at most R times the optimal cost, is an R approximation. Everything that we consider is a minimization problem, so the definitions are standard and they are common to in the community. A polynomial time approximation scheme is a family of approximation algorithms containing a 1 plus epsilon approximation for all epsilon that is strictly positive, and without loss of generality, I can assume, for example, that epsilon is an Egyptian fraction if I want. An efficient polynomial time approximation scheme is a subclass of the EPTAS, where the time complexity is upper bounded by a function of epsilon, or 1 over epsilon, times the polynomial in the input binary encoding length. Here, binary encoding length of the input is well defined. This function, in principle, is any function, but in theory, we require this function to be computable function. Whatever you could imagine will work. And AFPTAS is an EPTAS where this function is some polynomial or upper bounded by some polynomial. And since we consider a strong NP-hard problem, we don't expect to see an AFPTAS. Okay, I will not show you an AFPTAS for a strong NP-hard problem without stating a title saying P equal NP. Okay, so it's not like a hidden result, what we would like to see. Our problem, as well as any interesting special case of this problem, the scheduling variant, is strong NP-hard, so we don't expect to see an AFPTAS. There are also asymptotic polynomial time approximation schemes. These allow additive constants or additive terms, or slightly slower growing function of the optimal cost as an additive term. And here we require the approximation ratio to hold for inputs where the optimal cost is large. The optimal cost goes to infinity, and we require the approximation ratio to tend to something that is at most 1 plus epsilon. This is an AEPTAS, and then AFPTAS with this additional F is an AEPTAS where the running time is upper bounded by polynomial in the input encoding length and in 1 over epsilon. For strong NP-hard problem like beam packing and like our beam packing generalization, we may be able to establish an AFPTAS. And we are happy with this type of results. Okay, so I started by saying that this is a generalized variant of the extensible beam packing problem. There are special cases that were studied in the literature. For the first one is the extensible bin packing, where we have only one, where for the scheduling variant for all machines, we have that the fixed cost, the standard capacity, and the overtime cost are all one. For the bin packing variant, we have only one type for which this holds. This is useful. But here you need to assume that the machines are identical, roughly speaking. So in the scheduling variant, the machines are all the same. And you're able to schedule more jobs than what they fit into the standard capacity, but the cost grows linearly in the same rate. It was also studied if the bin sizes are not always the same. So extensible bin packing with the unequal bin sizes, although here it is written bin, it is still the scheduling variant, where for all machines, we have sigma I equal to 1. And using our assumption, this means that the fixed cost equals the standard capacity. And so if you're trying to schedule the jobs, you start trying to fill all the standard capacities, and afterwards, no matter where you put the additional jobs, they cost the same. If you're trying to generalize the extensible bin packing from the identical machine case, so it is the scheduling variant for the extensible bin packing, to the case of uniformly related machines, what you're going to get is that for all I, the fixed cost is 1, but the sigma I is 1 over the standard capacity, is the inverse of the speed of machine I. Okay, so the assumption that Fi equal to 1 is equivalent to assume that the machines are uniformly related machines. So these two cases in blue, nothing in blue, whatever, these were studied. The uniformly related machines case was not studied, and my generalization was also not studied before. What was known for the extensible bin packing problem, in the case where the fixed cost, the standard capacity, and the sigmas are all ones for all machines, that least scheduling is 5/4 approximation. LPT, the longest processing time algorithm, is 13/12. Alon Azar, Boginger, and Yadid, and I saw Yossi in the audience earlier than that, showed that this problem has an EPTAS. So they considered a variety of problems for which they showed the existence of an EPTAS. Although in their paper, the notion of EPTAS was not coined already, so they published before it was coined, but their algorithm is an EPTAS. And this family of mean-sum objectives for identical machines was also later considered by Janssen, Klein, and Schei, who got a better running time. So still an EPTAS, this is the best you could hope for, but the running time was improved for all these objectives of the mean-sum objectives on identical machines, considered by a running time. There is one additional result that Kaufman and Luker in SODA 2001, they showed an AFPTAS. So if you are allowed to have an additional additive term in the cost of the solution, then you are able to improve the running time from something that grows exponentially in 1 over epsilon to something that stays polynomial in 1 over epsilon. So although the problem is only NP hard, we still have a hope to get an AFPTAS. If the bin sizes are not equal and unequal, then LPT is known to have a 4 minus 2 square root of 2 approximation. This number looks very big, but it's not so large, so it's less than 1.2, so it's not so bad. And the EPTAS was obtained by Epstein and Tassa in where the journal version was published in Acta Informatica. Their scheme follows from a scheme for a larger family of problems where they have machines with asymmetric cost function. And these asymmetric settings give the EPTAS for extensible bin packing with unequal bin sizes. But you need to assume something about the asymmetry, because in absolutely asymmetric settings, you have a generalization of the minimum make span on unrelated machines, for example. Okay, so in order to get a scheme, you need to assume something about the structure of the asymmetry. And they assumed that the cost functions have a constant upper bounds on the Lipschitz constants, which means that they assumed in our settings that the ratio between sigma I and sigma I prime is bounded by a constant. For every pair, and the constants are common when we compare the ratio of two sigmas for two different machines. If you consider a uniformly related machine, this is equivalent to a bounded speed ratio. And for the case where the speed ratios are unbounded, they got nothing. For the bin packing variant, after I was convinced earlier this week that there are no earlier works, there is an easy case in which there is a bin type I, for which sigma I is at most the fixed cost divided by the standard capacity. And then you don't need more than one bin of this type. It doesn't help to have several bins of this type. If you had several bins of this type, you could pack all items that were packed into these bins into one bin of this type, and you will not increase the cost. So if there is only one type and the fixed cost and the standard capacity is 1, but the sigma is smaller than 1, then it is optimal to pack everything into one bin. So studying the extensible bin packing problem in terms of the bin packing possibilities of buying more machines is not really interesting, because you will pack everything into one bin and that's it. This is optimal. If there is only one bin, but the overtime cost, the sigma, is larger than 1, the problem becomes NP hard in a strong sense. So you will try to pack items into many bins and not paying much more than the fixed cost of these bins. Okay, the results. So I will show you an AFPTAS for the bin packing bond, and then I will go for showing you an EPTAS for the scheduling bond. The AFPTAS, this will be the first result because of two reasons. One is that this is easier, and the second, which is more important, this is the first talk of a bin packing seminar, so we need to do something with bin packing. The second result is more interesting, at least for me. Okay, so we start by the bin packing variant. We can have as many bins of each type that we want, but we are going to pay for these bins according to the cost function of the bin. So we already mentioned the fact that if the overtime cost is smaller than the fixed cost divided by the standard capacity, then these bins behave differently. We have only one bin of each type, of each such type, and we guess a bin type of minimum overtime cost, minimum sigma, that is used by the optimal solution, by a fixed optimal solution that we keep in mind. And among all bin types for which sigma I is smaller than Fi over Ci. If there are no such bins, then fine. Remember that there is not such bin, but otherwise we guess one piece of information about the optimal solution, that is the index k of a bin type for which this holds. And this bin type has exactly one bin. We don't know the total size of items assigned to that bin, but it has exactly one bin. And the optimal solution, as well as our algorithm, will pay the fixed cost of bin type k exactly once. And we will be able to put the items into this bin without paying too much. For all other bins of other types, we have that the total size is at most 3 times the standard capacity, and the cost based on this total size assigned to such a bin is at most 3 times the fixed cost. Why is that? Because if we have an item that doesn't fit at all into the fixed capacity, we could move it to the machine to the bin of type K. And furthermore, we can partition the bins of the one bin. We can partition to several bins of the same type, while decreasing the cost of the total this collection of bins. Okay, so in this way, we are able to bound the used capacity of a bin and the cost of these bins in terms of 3 times the fixed cost and the standard capacity. Okay, so what we do with this information, we scale. We scale the standard capacity and the sizes of items by common multiplicative factor. In this way, we don't change the ratio between the total size of items assigned to a bin and its standard capacity. And we do this in order to guarantee that the maximum standard capacity as well as the maximum item size are at most 1/3. Okay. In order to not change the cost of a solution, we need to scale the fixed cost and the overtime cost by 1/s. In this way, whatever solution we have in mind keeps exactly the same cost as it used to be in the original instance. I add another bin type of a standard capacity 1/3 and one of the overtime cost simply by using a bin type of the original instance. So I define what will be the cost of having a standard capacity of 1/3 of one of the bin type. Second, we do another scaling step where we scale the fixed cost and the overtime cost in order to assume that the maximum fixed cost is 1. 1 is a special has a special role because I would like to have an additive term in the cost or in the bound of the cost of the algorithm, like saying that the cost of the algorithm is at most 1 plus epsilon times the optimal cost plus an additive term. And this additive term is multiplied by 1, which means that I change the definition of asymptotic polynomial approximation scheme to be depending on the maximum fixed cost. This is the one in the asymptotic definition of AFPTAS. If you try to avoid this assumption, it's impossible, basically. You cannot do anything. In order to approximate the problem that we get after the 2 scaling steps, I'm going to use an auxiliary problem defined as bin packing with bin utilization cost. And I have a good reason to do that, because in 2017, and I have published an AFPTAS for this problem. Okay, so we're going to use an existing asymptotic polynomial time approximation scheme to a different problem. This different problem is defined using a monotone non-decreasing non-negative cost function pi, defined over the interval between 0 and 1, and a set of items 1, 2, up to n, where item j has a non-negative size sj, once again between 0 and 1. A feasible solution is a partition of the items into subsets, where every subset fits into a unit size bin. But the cost we are paying for such a bin is the pi value of the total size of items packed into this bin. And we showed an AFPTAS for this problem using 2 approximated evaluation operators under the assumption that these are good approximation, and they always return answers with polynomial number of bits. This polynomial number of bits may sound really strange condition, but these are actually crucial because evaluating the function pi, that is the square root, is impossible. Even if you try to evaluate the function for a set of items of total size 1/2. assuming that you want an algorithm that runs in the RAM model. So in order to avoid such problems with square root and stuff like that, you need to deal with the oracles that don't return your exact solutions, but an approximated one. In order to transform our instance to the bin packing with bin utilization cost, what we do is we use the same set of items as we did after the first and second scaling step. The second scaling step doesn't change the set of items. And for every value of x, we define the cost of x as the minimum of all bin types, cost of using one bin of this type for packing total size of x. This is well defined, but we do a small modification for this rule, is that for the bin of type k, the one with the minimum sigma among the ones that satisfy this condition, this cost of packing x using one bin of type k is changed to sigma k times x. So I ignore the fixed cost and then simply put the total size of x on top of the standard capacity. And we note that pi, as well as the inverse of pi, can be evaluated exactly in linear time by traversing the list of bin types. So we are able to use the AFPTAS for bin packing with bin utilization cost. And in this way, we get immediately the AFPTAS for bin packing variant of the generalized extensible bin packing. Okay. So this concludes the bin packing variant. And I would like now to move to a different scheme for the scheduling variant. So the set of machines is given, and we need to assign the jobs to the machines in a way that the total cost, in terms of this cost I, is minimized. The scheme has several steps. Some of these are easy, some of these are not so easy, and some of them looks really suspicious, like this n-fold programming formulation. Okay, so you have a list here of steps to expect, but let me try to give you a clue what goes into this scheme. So the first steps is the scanning steps. I would like to structure the input in a way that will be easier for the future steps of the algorithm. The first scanning is to ensure that the minimum of sigma over all machines is 1. And I denote the machines that attain this minimum, one of these machines, is H. So machine H has minimum sigma, and this minimum sigma is 1. This is done by, if the minimum is X, then we change the instance in a way that we multiplied all sigmas by X and all the standard capacities and the sizes by X. In this way, we keep track of the assumption that the fixed cost is equal to the product of sigma and C, and the cost is the same no matter what is your solution. So you keep the same cost for every solution, so this scaling is without loss of generality. The assumption that I would like to use, this is not really scaling, this is just renumbering the machines, is that C1 is at least C2 and so on up to Cn. So if the instance doesn't satisfy these, then I reorder the machines in this way. The second rounding step is to round the size of jobs. And we need to round those slightly. So we will decrease the number of different sizes. We could do this either geometrically to the next integer powers of 1 plus epsilon, or if the processing size is between epsilon to the I and epsilon to the I minus 1, then we could round pj to the next integer multiply of epsilon to the power of I plus 1. It doesn't matter. So the two rounded instances will not be the same, but both of these will work. And it is a standard tool to say that if the processing time of a job increases by at most a factor of 1 plus epsilon, then the cost also increases by at most 1 plus epsilon. For our problem and many other problems. The next step is to structure the output that we are looking for. Okay, so instead of looking for the optimal solution or something that is close to the optimal solution, I would like to make additional assumptions on the optimal solutions. And I use the term nice whenever I have such a step. Okay, so this nice is a standard phrase I'm using in cases where I would like to add more assumptions on the output that I'm looking for. And the feasible solution for this problem is called nice if for every machine I that is not H, the one that is not the minimum sigma, the total size of jobs assigned to I is at most Ci over epsilon. Not too large with respect to the standard capacity. So for the big packing problem, I assume that the total size of items is at most 3 times the standard capacity. Here, I allow more to be there. And the claim is that the best nice solution costs at most 1 plus epsilon times the optimal cost. And the reason is that if we have an optimal solution and every machine that doesn't satisfy the condition, then I move all jobs assigned to such machine to machine H. And in this way, the cost is increased by at most the total fixed cost of the machines that did not satisfy the condition. And this is at most epsilon times their total cost in the optimal solution. So in this way, I'm able to upper bound the total size of jobs assigned to a machine, except for machine H. Machine H is unbounded total size of jobs assigned to it. The next step is to use the shifting technique. For uniformly related machines, I would like to consider the sub-instances where the speed ratios are at most constant. So this is the goal. For the generalized problem, I need to define this differently. So I would like to use the CIs and then to partition the instance into sub-instances where the CI are similar in a common sub-instance and very different in different sub-instances. In order to do that, I will delete machines from this. Deleting machine means that I will not assign anything to these machines. I could not decide to delete machine H, but other machines I could decide to delete. And in order to do that, I look on the CIs and I define a multiplicative gap between sub-instances in order to not change by a lot. I do this for the value of t that minimizes the total fixed cost of machines in end of t. And I take an optimal solution that is allowed to place jobs on all machines and place everything on the deleted machines to machine H. And then if I do that, the cost of the solution is increased by this sigma of Fi of machines that were deleted. As a consequence, I'm able to partition the machines into consecutive subsets of machines, where in every subset, the standard capacities is similar up to some small constant, like 1 over epsilon to the power of order of 1 over epsilon. And if I have different subsets, then there is a multiplicative gap of 1 over epsilon squared. Based on this partition into subsets of machines, I also define partitions of the job set, where each job is assigned to a machine subset with smallest capacities, where if I decide to scatter the job on one of the machines of these capacities, then this is doable in a nice solution. So I have this upper bound of the sum capacity divided by epsilon, then this controls the upper bound on the sizes of jobs that are able to be assigned to one partition of the machine. The problem is that not all the jobs are covered by this rule, so the jobs larger than the maximum standard capacity divided by epsilon are allocated to machine H and deleted from the instance. They cannot be assigned elsewhere, and this adds a large total size to machine H. But this is a correct decision in nice solution. So we could restrict ourselves to such settings. And then I would like to solve each sub-instances independently of the others. Unfortunately, it's impossible. And in order to, I need to be able to move jobs from one subset of machines to the next one, the one that uses larger standard capacities. But I need to control only the total size of these jobs, because all these jobs will be scheduled on the subset of machines of the larger standard capacities as very small jobs. So they are kept sent. So at the last step, I will use dynamic programming to decide what should be the total size of small jobs that are moved from one sub-instance to the next one. So we need to solve a sub-instance where we have also a additional total size of small jobs that are entering from a sub-instance of smaller total atomic capacities. And we have also a total size of jobs that are moved to the next one. And in order to do that, I need to solve auxiliary problems, where the auxiliary problem is given the set of jobs of size that are at least epsilon fraction of the smallest capacity, smallest atomic capacity of the sub-instance. And I have also a volume of this sand that I get from the earlier problem, and a different, perhaps, volume that goes to the next sub-instance. The sand means that I allow temporarily to schedule these very small jobs fractionally, but transforming this fractional allocation of small jobs into integral allocation doesn't really change the approximation ratio. Furthermore, the size of the sand that I allow to schedule on each machine, the sub-instance, is an integer multiplier of epsilon fraction of the smallest capacity of the sub-instance. Once again, you could add this epsilon fraction, and it will not change the cost too much. And assuming that we can solve the auxiliary problem polynomial time, then all we need to do is to put the formulas into dynamic programming and get the corresponding solution to the original instance in polynomial time. And in order to solve the auxiliary problem, I would like to formulate an integer program to do that. Now I need to check who's my audience so far. Okay, so we have different backgrounds. So we'll try to do it smoothly for the non-expert. And I apologize from for the experts that will be bored. Okay. So enfold programming is one type of integer programs for which nowadays we know how to solve in polynomial time. And this has some applications, not so many, but we know how to do that. If you know something about integer programs that can be solved in polynomial time, there are two main cases. One is that the number of variables, the dimension of the integer program, is constant. And this settings was solved by Lenstra in 1981, I think. The other case is that you have a constant number of rows in the constraint matrix, like a d-dimensional knapsack for constant p. But then you need to assume that the numbers in the constraint matrix are small integers. Enfold programming is a slight generalization of this constant number of rows. And it is defined if you have the following characteristics. So there is a constant number of global constraints. Add to that box constraints on the variables, meaning a lower bound and an upper bound for every decision variables. In addition to these global constraints, I have also a partition of the decision variables into local collections. So a variable may appear only in one local collection. And each local collection may have additional constant number of constraints that involve only the decision variables of this local collection. Assuming that you have such a constraint matrix and all numbers that are non-zeros are small integers, small into absolute values, then we nowadays know how to solve it in polynomial time, where these constants that appear everywhere are some sort of parameters that appears in the exponent of the running time, but it has the flavor of running time that is allowed in EPTAS. So how do we get such settings? So our decision variables have two families. The first one is the XIC, that is an indicator variable for using configuration C for machine I, where a configuration is a vector encoding the set of the number of jobs of large jobs assigned to I and the size of stand assigned to I. Since we have this lower bound and upper bound on size of jobs that could be assigned to a machine in this sub-instance, then the numbers of large jobs of each size are bounded by constants. And second, the family of decision variables is the YP for every size in the sub-instance of jobs. It encodes the number of jobs that are left unassigned, and then they moved as a send into the next sub-instance. We have the global constraint saying that each job, that is either job or unit of stand, is either scheduled on one of the machines during the selected configurations, or it is part of this YP. So we have the sum over all I and C of the number of jobs of size P assigned in configuration C to machine I plus YP is the number of jobs of size P in the instance. And the constraint is for every size, but this number of constraints is constant because we have only constant number of constraints, constant number of sizes. And we have also one additional constraint bounding the total size of unassigned jobs of send. That is the sum of the PYP is the given upper bound, this sub-instance. In addition to these global constraints, we have local collections, and the local collection corresponds to one machine, one specific machine. So for every machine, we have a constraint saying that we are allowed to use exactly one configuration for that machine. So the sum of all C of XIC of configuration C assigned to machine I is equal to 1 for every machine. So in this way, we created a partition of the decision variables into local collections, and we have one constraint for each local collection. In addition, all variables are non-negative. We don't have upper bounds constraints, but this is a formulation of N4 programming, more exactly as the generalized N4 programming, but this generalized N4 programming, by now, they have the same time complexity at the moment as N4 programming. So, other questions? So Janusz decided that the speaker will collect the questions. I will collect the questions now. Okay. So unless there are any further comments, I will conclude this.
I have a short question, Asaf. That's what do you think about the problem with about scheduling with machine cost? How does it fit in the picture?
Scheduling with machine cost.
That means that you have the possibility to buy a machine always by a fixed cost.
You could schedule whatever you want.
Yeah.
Yes. You need to assume something about these cost functions. So in principle, you don't once again, what is the problem? You have different types of machines. You're able to buy as many machines of each type that you want. Each machine has a different cost function.
Yes. Yes.
And this is exactly the bin packing with bin utilization cost.
That's a scheduling, so that you schedule the jobs, and whenever you want to, you can buy a new machine if you think that the machines you have already are overloaded.
Okay, the difference between the scheduling and the bin packing set of problems is that in the scheduling problems, you are given the set of machines in advance and you cannot modify it.
Yes.
In the bin packing problem, you are able to modify those.
Yeah. Yes.
Okay.
So that's somewhere in between.
Somewhere in between. And you want to pay for the machines that you are given in advance or not?
You can start with 0 machines, so that naturally for the first jobs you will buy a machine, and then you decide.
And then you would like to consider exactly the type of cost functions that I mentioned.
Yeah.
It's exactly the bin packing with bin utilization cost.
Yeah.
There is an AFPTAS. I like it a lot, but we already published it.
You pay for the machine, but you don't pay for
the
make span. Not the make span, the completion time of the machine. You pay for the make span, and not for the completion time of the machine.
So you pay only for the make span objective.
Yeah.
Okay.
Offline?
Offline?
Online?
Okay, online is something else. Offline, you could guess the make span and then deal with that. Okay, so and then you have a fixed make span, and you try to minimize the number of pins. This is bin packing.
But the make span is actually not well defined, because the number of machines is different. So that first you can think about offline problem too, naturally.
Okay, so you could guess within a multiplicative factor of 1 + epsilon the make span that is used in one specific optimal solution. Okay, offline, you could do that. And then you restrict yourself to the solutions that don't use the bins with the total size of items that is larger than this amount. And you try to minimize the number of bins. So you first guess the make span in a fixed optimal solution, and then you apply your favorite approximation algorithms for the resulting bin packing instance. This is offline. You could not do this in online settings. And I don't know.
Okay. Thank you.
So,
Thank you.
I don't know how to invent a new result.
Okay.
No questions? So I sincerely apologize from the expert of the end for this terrible dispute.
Sorry, I have maybe an nasty question. So do you think it's possible to generalize your techniques to, let's say, other functions than linear, like convex functions or something like that?
Convex functions. First, you have this problem with the inability to evaluate convex functions in constant time. Okay, but assuming that you're able to solve this by something, the problem is that you need to do something else. So everything works, and then as long as you're able to restrict yourself to something that is similar to nice solutions. Okay, for the scheduling problem, for the bin packing, you need to upper bound the total size of the items assigned to one bin. Okay. For convex functions, this is doable. For very strange functions, this is not doable. And they don't have a clear clue how to investigate the cost function in polynomial time. So you need some sort of structures in order to be able to say, if you have a bin of this total size, then I replace it by 5 bins of 1/2 total size. If you're able to do that, then you're able to do something. If you're not able to do that, then you're stuck, basically. Okay, so for the scheduling problem, very convex, but very steep function, you are not able to do anything. For the bin packing variant, convex and nicely shaped, you could do things. Okay, but you need a way to say, I'm considering only these functions, and then I'm able to prove this upper bound on the used capacity of a given bin. Otherwise, the notion of one is undefined. No questions?
Sorry, I have a question. Does there have a difference if we consider the item size or job size? For example, like the maximum size of the job is smaller than the minimum size of the capacities.
Yes. So for the bin packing problem, you usually assume that the sizes are at most 1. And this is a part of this one that is global constant in terms of the cost of in the asymptotic approximation schemes settings. For the scheduling problem, you don't assume any upper bound on the processing time or the size of the job. If you have another bound, you could use that. If not, then you're stuck without being able to define this global constant of 1.
So does it help to analyze the?
Yes, it's a matter of an analysis. It doesn't appear anywhere in the algorithm as well. Only the matter of analysis depends on the cost of packing one item, the largest one item.
Okay, thank you.
Okay, so when you put bounds, this larger size of one packing one item appears. Will the slides be available on the website? Okay, so Marina, I have no idea, so I'm not controlling the website. So,
if you send it to me, I'll
definitely can send you the slides. I try to record as well, which means that if it works, I can send I can upload the video file and send the website manager the link for the videos, and they can do a report. So I can send the slides and do that. If you don't get the slide, then ask. Okay, so they are not pilot.
Okay. Good. I think that there are no more questions, so that I would like to thank you, Asaf, for very nice talk and answering the questions. And the next speaker will be Professor Arindam Khan next week at the same time. Thank you for coming.